Welcome back. We'll be continuing some basic results on topological vector spaces. So let us start with a simple theorem. Let X be a TVS. Let X be a TVS. Okay. Let X be a TVS. Let A and B be subsets of X. Subsets of X. Then A closure plus B closure is a subset of A plus B whole closure. B, if C is a convex subset of X, a convex subset of X, then C interior and C closure are convex. C, if B is a balanced subset of X, then B closure is balanced. Moreover, if 0 belongs to B interior, then B interior is also balanced. Okay. So proof of A. It's very simple. So let X belongs to A closure and Y belongs to B closure, then X plus Y will belong to A closure plus B closure. So we need to show that every neighborhood of X plus Y intersects with A plus B. If we show that, then we are done, right? So let V be a neighborhood. Let V be a neighborhood of X plus Y. By continuity of addition, there exists neighborhoods V1 and V2 containing X and Y respectively, right? There exists neighborhoods V1 and V2 containing X and Y respectively, such that V1 plus V2 is contained in B. This is because of the because of the continuity of the addition, right? So now, since X belongs to A closure, A intersection V1 is not empty, right? This is because it belongs to the closure. This is by the definition of an element belonging to the closure. And since X and since Y belongs to B closure, B intersection V2 is also not empty, right? This is also not empty. So let U belong to A intersection V1 and V belong to B intersection V2. Then U plus V belongs to A plus B intersection V1 plus V2, right? And we know that V1 plus V2 is contained in V, right? V1 plus V2 is contained in V here, right? V1 plus V2 is contained in V. Hence A plus B intersection V is also not empty. This implies X plus Y belongs to A plus B whole closure, right? A simple proof. Moving on to show B. So let us first show why C closure is empty. To show C closure is empty, we first it's given that C is convex to show C closure is convex, right? So we need to show, so let T belong to closed interval 0 1 to show T times C closure plus 1 minus T times C closure is contained in C closure. Now since MT, where MT is this map x going to x, MT of x equal to T times x, and M1 minus T is similarly like M1 minus T of x is 1 minus T times x. These are homeomorphisms, right? Since these maps are homeomorphisms, T times C closure will be equal to T times C whole closure, and 1 minus T times C closure will be equal to 1 minus T times C whole closure, right? This is because of the fact that these two maps are homeomorphisms. So we get that T times C closure plus 1 minus T times C closure is equal to TC whole closure plus 1 minus T C whole closure, which is contained in C closure. Why? Because TC plus 1 minus TC is contained in C, and the closure is again, right? Is that okay? Oh, sorry, that's not because of that. Sorry, it's because of the previous A. Sorry, yeah. So this containment follows from A, right? It follows from A. Okay, let me show how. So this is equal, and this is contained in TC plus 1 minus TC whole closure by A, and since C is convex, TC plus 1 minus TC is contained in C, hence we get this is contained in C closure, right? So we showed that if C is convex, then C closure is convex. Similarly, we have to show C interior is convex. So note that T times C interior plus, again T belongs to closed interval 0 1, T times C interior plus 1 minus T times C interior is contained in C, right? Because C is convex, right? You note that this is an open set, right? T times C interior plus 1 minus T times C interior is an open set, and C interior is the largest open set contained in C. Hence T times C interior plus 1 minus T times C interior is contained in C interior. Is that okay? T times C interior plus 1 minus T times C interior is an open set, right? That's again because of the fact that this MT and M1 minus T are homeomorphisms, right? C interior is an open set, T times C interior is an open set, then 1 minus T times C interior is also an open set, right? It follows from that, and sum of two open sets is open. So we get that this is an open set which is contained in C, and C interior is the largest open set contained in C, hence any other open set contained in C must be contained in C interior. So we get that T times C interior plus 1 minus T times C interior is contained in C interior. So C interior is also convex. So moving on to prove C, we need to show that B closure is balanced, right? So given B is balanced, to show B closure is balanced, so let alpha belong to K such that mod alpha is less than or equal to 1, then C times B closure is equal to, alpha times B closure is equals to alpha B whole closure, right? This is again because this M alpha map from X to X, where M alpha of X equal to alpha X is a homeomorphism. So this equality follows from that, right? Since this map is a homeomorphism, we get that alpha times B closure is equals to alpha B whole closure, and this is contained in B closure because alpha B is contained in B, right? Now we take closure on both sides, right? So since alpha B is contained in B, alpha B closure will be contained in B closure, right? So we get that B closure is balanced, right? Next, suppose 0 belongs to B interior. To show B interior is balanced, right? To show B interior is balanced. If alpha equal to 0, then 0 times B interior is nothing but singleton 0, which is contained in B interior, nothing to prove. If alpha is non-zero and mod alpha is less than or equal to 1, alpha belonging to K, then alpha times B interior is again by the fact that this map is a homeomorphism, this M alpha is a homeomorphism, we get that alpha times B interior is nothing but alpha B whole interior, right? Alpha B whole interior, and since alpha B is contained in B, alpha B interior will be contained in B interior, right? So this is contained in B interior. So this shows that B interior is balanced. This shows that B interior is balanced, right? This was a simple theorem. So moving on, next we'll be proving two important theorems. Let X be a TVS. Then every neighborhood of 0 contains a balanced neighborhood of 0. Balanced neighborhood of 0. Okay. So proof. Let V be a neighborhood of 0. So we need to show that there exists a neighborhood W of 0 such that W is contained in V. Okay. So to do that, we use the fact that scalar multiplication is continuous. So we know that 0 times 0 is equal to 0. Here this 0 is a scalar, this 0 is a vector which is equal to the vector 0, right? So we know that 0 times 0 is 0. By continuity of scalar multiplication, continuity of this dot, there exists R positive and a neighborhood of 0, a neighborhood say G of 0, such that for every alpha in K with mod alpha less than or equal to R, alpha times G is contained in V. This is nothing but this is all this we get from continuity of scalar multiplication, right? Okay. Now consider W equal to union of all this G alpha where mod alpha is less than or equal to R, right? Each of these G alphas are open sets because G is open, right? Not each of them, for all the non-zero alphas, right? Whenever mod alpha is less than or equal to R, alpha non-zero, G alpha is a neighborhood of 0, right? And when alpha equal to 0, alpha G will be nothing but singleton 0, right? That doesn't matter. So each G alpha is a neighborhood of 0, 0 already belongs to alpha G. So we get that W is a union of union of alpha G, and W is open. Right? It's open because it's a union of open sets, except when alpha is 0, and that doesn't matter because 0 already belongs to each of the other alpha G's, right? So W is an open set containing 0. Now we show that W is balanced. To show W is balanced, and note that each G alpha is contained in V, so this union of G alpha is also contained in V, hence this W is contained in V. So if we show W is balanced, then we are done. So to show W is balanced, right? So let beta belong to K such that mod beta is less than or equal to 1. Then what happens to alpha times W? Alpha times W will be beta times W will be beta times union of mod alpha less than or equal to R alpha G. This is equal to mod alpha less than or equal to R beta alpha G, right? Beta alpha G. Now beta alpha G, okay, note that mod beta times alpha is equals to mod beta times mod alpha, which is less than or equal to R, right? So this implies beta times alpha G is contained in W, right? This is one of the elements here in the union, right? Beta times alpha is one of the elements in W. So this implies union of beta times alpha G mod alpha less than or equal to R is contained in W, but this is nothing but beta W. So we showed that beta times W is contained in W. Hence W is balanced neighborhood of V. Okay. So moving on, next theorem. Let X be a TVS, then every convex neighborhood of 0 contains a balanced convex neighborhood of 0. Contains a balanced convex neighborhood of 0. Is that okay? So proof. Let V be a convex neighborhood of 0. By previous theorem, there exists a balanced neighborhood W of 0 such that W is contained in V, right? This is by the previous theorem. Now consider A equal to intersection of alpha V mod alpha equal to 1. Okay, A is the intersection of all such sets mod alpha times V, where mod alpha equal to 1. Okay, claim that, okay, before that, so let mod alpha be equal to 1, then I claim that alpha times W is equal to W. This is a simple claim. So since W is balanced, alpha times W is already contained in W. One side is already true because W is balanced. To show that W is contained in alpha W. Now since mod alpha equal to 1, mod alpha inverse is also equal to 1, right? And again, since W is balanced, alpha inverse times W is contained in W. Okay. Now let X belong to W, then alpha inverse times X belongs to alpha inverse W, which is contained in W. This implies alpha inverse times X belongs to W. Hence alpha times alpha inverse, hence alpha times alpha inverse times X belongs to alpha W, but this is nothing but X. This implies X belongs to alpha W, right? Thus alpha W is equal to W. Okay, right? Alpha W is equal to W, and this W is contained in V. So alpha W, this W which is equal to alpha W is contained in alpha V for every mod alpha equal to 1. This implies this W is contained in intersection of alpha V mod alpha equal to 1. Did you understand what we did here? Right, W is contained in V. This implies alpha times W is contained in alpha V, right? But this alpha W is nothing but W. So W is contained in alpha V for every mod alpha equal to 1. This implies W is contained in intersection of alpha V where mod alpha is equal to 1, right? So this is what we have done here. So W is contained in intersection of alpha V mod alpha equal to 1. This is nothing but our A. This implies W, and W is an open set containing 0. So W is contained in A interior and 0 belongs to A interior, right? W is contained in A interior and 0 belongs to A interior. Note that alpha V is convex for every mod alpha equal to 1, right? It doesn't matter. Since V is convex, alpha V is convex, right? And intersection of convex sets is convex, any intersection, arbitrary intersection. So alpha V, intersection of alpha V mod alpha equal to 1, that is A is convex. You can easily show that arbitrary intersection of convex sets is convex. So since V is convex, alpha V is convex, and intersection of all these alpha V is convex, that is our set A is convex, and we already showed that if A is convex, then its interior is convex. So hence A interior is convex. So we got a convex neighborhood of 0, right? That is A interior. Why is A interior contained in convex neighborhood of 0? That is A interior. So why is A interior contained in V? That's simple, right? That follows from the definition here, right? A is equal to intersection of mod alpha equal to 1 alpha V, which is contained in V, right? Which implies A interior is contained in A, which is contained in V. So we got a convex neighborhood of 0, which is contained in V. So if we show A interior is balanced, then we are done. If we show A interior is balanced, then we are done, right? So to show that it's enough, to show A interior is balanced is enough if we show A is balanced, right? Since 0 belongs to A interior, it is enough to show A is balanced, right? It's enough to show A is balanced. Why? Because it follows from our previous theorem here. It follows from this previous theorem, not previous, the one before that, this one. So if B is balanced, then B closure is balanced. Moreover, if 0 belongs to B interior, then B interior is balanced. So in our case, we already know 0 belongs to A interior. We already know 0 belongs to A interior. So if we show A is balanced, then it would automatically imply A interior is balanced, and that would complete the proof of the theorem. So our next aim is to show A is balanced. A is balanced. Here we will be using the fact that A is convex. Here we will be using the fact that V is convex. Okay. So how do we do that now? So let beta belong to K such that mod beta is less than or equal to 1. If beta equal to 0, then 0 times A is singleton 0. 0 times A is singleton 0, which is contained in A, right? There is nothing to prove then. So let mod beta be less than or equal to 1 and beta is non-zero. Then we can write beta equal to R times gamma, where 0 is strictly less than R, less than or equal to 1, and mod gamma is equal to 1, where gamma belongs to K, right? We can always decompose beta like this, right? So beta times A is equals to beta times intersection of alpha V mod alpha equal to 1, which is equals to intersection of beta times alpha V mod alpha equal to 1, which is equal to intersection of R times gamma times alpha times V mod alpha equal to 1, right? Note that mod gamma times alpha is equals to 1, right? Mod gamma times alpha equal to 1. So we can change this index, right? Multiplying by gamma will again cover the whole unit sphere. Here we are taking the intersection over all the units, over the entire unit sphere. So by multiplying by gamma, we are again covering the whole unit sphere. So this is nothing but intersection of mod delta equal to 1 R times delta times V, right? We are just changing the indexing set. Or we are not changing the indexing set, we are just changing the index, right? The index is the unit sphere. So if we show R times delta V is contained in delta V for all mod delta equal to 1, then we are done, right? If we show this, then we are done, because this would imply intersection of R times delta V mod delta equal to 1 is contained in intersection of delta V mod delta equal to 1. This is nothing but A, and this is nothing but here B. This is nothing but beta times A, which is contained in A. So if we show this, then we are done, right? So let X belongs to delta V, then X by delta belongs to V, right? X by delta belongs to V. Now since V is convex, R times X by delta V plus 1 minus R times 0 belongs to V, right? 0 already belongs to V, it's a neighborhood of 0, and R is a number between 0 and 1, right? So by convexity of V, R times delta X plus 1 minus R times 0 belongs to V. This implies R times X by delta belongs to V. This implies Rx belongs to delta V, right? Rx belongs to delta V. Note that Rx is an element of R delta V. So we showed that any element of R delta V belongs to delta V. This implies R delta V is contained in delta V. Hence, beta times A is contained in A, which implies A is balanced. A is balanced. This implies A interior is balanced and A interior, okay, A interior is balanced, convex neighborhood of 0 contained in V. So this completes the proof of the theorem. So we have shown that every convex neighborhood contains a balanced convex neighborhood of 0, right? Okay, so moving on, next theorem. Let X be a TVS and let V be a neighborhood of 0. Let 0 less than R1 less than R2 etc. be a sequence of real numbers such that Rn tends to infinity as n tends to infinity, then X is equal to union of Rn times V, n varying from 1 to infinity. In other words, V is absorbing. That is, every neighborhood of 0 is absorbing. Okay. So how do we prove this? So let X belong to X. I have to show that X belongs to Rn times P for some n, right? So define two functions. Define f from k cross singleton x to x. Now x is fixed, okay, let X belongs to X, we are fixing an X. So let f from k cross x to x be defined as f of alpha comma x is equals to alpha times x. F is continuous, right? Because f is a restriction of the scalar multiplication map, right? We are restricting the scalar multiplication map to x cross singleton x. So this f is continuous, and you define g from k to k cross singleton x as g of alpha equal to alpha comma x, right? Clearly g is continuous because the coordinate map, the first coordinate is just identity map, alpha going to alpha, and the second coordinate map is alpha going to x. It's a constant map. So clearly the coordinate maps are continuous, hence the full map g is continuous, right? So f and g are continuous functions. Consider the composition of these two functions. Consider phi, which is defined as f composed with g, map from k to x, where f of alpha equal to f of g of alpha, which is equals to alpha x. So this phi is a continuous map from k to x, right? Phi is a continuous map from k to x. Since V is open, phi inverse V is open in K. Since 0 belongs to V, we have 0 belongs to phi inverse V. So given that it's given that Rn tends to infinity as n tends to infinity, right? Rn tends to infinity as n tends to infinity. This implies 1 by Rn tends to 0 as n tends to infinity, right? 1 by Rn tends to 0 as n tends to infinity, and we know that 0 belongs to phi inverse of V. So, by the definition of convergence, convergence of a sequence, there exists an n in n such that 1 by Rn belongs to phi inverse V for all n greater than or equal to n. This implies phi of 1 by Rn belongs to V for all n greater than or equal to n. This, by the definition of phi, gives us that 1 by Rn times x belongs to V for all n greater than or equal to n. This implies x belongs to Rn times V for all n greater than or equal to n, right? So this implies x is equal to union of some Rk times V, k varying from 1 to infinity. Again, this clearly shows that V is absorbing, right? There is nothing more to prove. This shows that every neighborhood V of 0 is absorbing. So this completes the proof. So we'll continue in the next class. Thank you so much.